Okay, so there are a number of cases where people do use Lagrangian tracers for revealing fluid motion. And I've shown a couple of pictures here from a movie that some of you may remember called Twister from 25 years ago. If you've ever seen it, you might remember that they drive into a tornado and they see a cow flying past them. And so here's a great example of a piece of material of constant identity, i.e. in this case a cow, and we're revealing locally the fluid motion by looking at the displacement of that object. As you might remember, the goal of the movie, in fact, is to release a series of objects into the heart of a tornado to follow it, and then they use a series of little elements like that to reveal the velocity and temperature field inside a tornado. So you can take a look at these YouTube links and see them directly. Another example that I'll show here is a time-lapse movie of Amsterdam Harbor. So here in Amsterdam Harbor, each of these individual boats is a Lagrangian element, and yet your eye is kind of easily getting an idea of the local flow by integrating where these points, these material points, go as a function of time. And this gives you some idea of the difficulty of a Lagrangian description, because we have to specify the initial location of every single one of these points, as well as where they go at all future points in time. So typically we won't use the Lagrangian description very much in fluid mechanics. Another example of a Lagrangian description is given by this example from the Hansa Carrier. The Hansa was a container ship that was actually traveling from Korea to the United States in 1990. It hit a very big Pacific storm, and 21 containers of Nike sneakers were washed overboard off the edge, and the containers broke open. Now, these sneakers were individually labeled with serial numbers, and so even though the storm happened in May of 1990, people found that they started to wash ashore and float ashore, and people started recording the dates of where they washed ashore and where they, what day and what time they were recorded. And so this allowed people to use a series of Lagrangian tracers, in this case sneakers, to map out a large-scale description of the flow in the North Pacific. And so here's an overview of it. The first sneakers were found near Vancouver, but then progressively later on they were found along the California coast. And finally, in fact, some sneakers were even found in Hawaii almost more than 2 years later. And this allowed people to get some idea of the large-scale recirculation in the Northern Pacific. And this is what's called a gyre. And a gyre is just a large recirculating eddy that comes from the interaction of the wind and planetary motion on the ocean. Now, an unexpected maybe corollary of this is that you may have heard of something called the Great Pacific Garbage Patch. So instead of sneakers, the Pacific Garbage Patch is collecting floating plastic. It's currently up to something over 87,000 tons of plastic, and it can be revealed by imaging satellites. This is the density of plastic in the ocean in 1962. By the time we get to 2018, there are these large regions where plastic is beginning to accumulate, and so this is at the center of one of the gyre of the large recirculation. Now, when I call this a garbage patch, it doesn't look like a floating mass of land. It's really just a collection of thousands and thousands of tons of small floating pieces of plastic, microplastic, and floating bottles. But this gives an idea that Lagrangian tracers are a very good way of revealing large-scale slow motions in the ocean. A final example that I'll use that's very up-to-date, in fact this is just in this week, is smoke here is being used as an imaging technique to look at the location of what's happened from the forest fires in the Pacific Northwest. And you can see that in fact the smoke from the fires that are along the seaboard here has flown out following the local velocity field, and you can reveal the atmospheric motion from where the smoke has gone. So finally we'll think about use of other kinds of imaging techniques that we just talked about on the board. And in the Eulerian reference frame, then a particularly useful way of doing things is by using the motion of individual particles. So what we're showing here is examples of path lines, where we can see the length of the path line is telling me something about the local velocity field. Here, in this case, this is a bubble rising in a tube, and hopefully you can see that the fluid is being displaced in front of the bubble and being replaced placed from behind. So this is the instantaneous velocity field, and your eye is probably constructing streamlines from this. But of course, they're going to look different at every instant in time as the bubble rises. The benefit of the Eulerian description is that we can frequently find a way of turning this into a steady problem. And the way to turn this into a steady problem is to remove the velocity of the bubble, which is upwards. So if we remove the velocity from the bubble, we subtract a velocity that's uniform everywhere in this frame, then the same velocity field now looks like this. And so this is the same flow, but now the fluid is coming in from the top. It's flowing past the bubble, so the velocity is largest here, and then it flows out. And just to emphasize, these are exactly the same velocity fields. But this is what we've done is we've changed our frame of reference, and so the benefit of the Eulerian description is that we now have a steady problem that we can think about describing. I'm going to show two other small examples of this for a more complicated time-varying flow, for which it's better to use video animations. So here's an example to image flow past a cylinder. And the flow past a cylinder here is going to be labeled by looking at the local temperature of fluid. And so what we're going to follow is really a series of streak lines or streak patterns, which is where the fluid element that's passed close to the cylinder has been heated, and we can explore where the hot fluid goes as a function of time. And so we can see that the streaks move downstream with the local velocity. You can see that there's hot fluid behind here, and you can see that this is clearly an unsteady flow. The region of hot fluid is growing as things increase in time, and eventually we'll find that in fact that these things can actually become even time dependent. And so as we go on down here, you'll see that the flow will start to become time dependent. But these ideas of following labeled pieces of material give us a very, very good way of seeing where particular material elements have gone. And if instead I try and reveal the streamlines for that, then here's an image of the streamlines for a flow that looks like that, where we can see the streamlines coming in from the left, so they enter our flow domain. The streamlines do not disappear or end, they exit the flow domain. And we can see that the flow instantaneously looks like this, but the velocity field is time dependent. So at every instant in time, the streamlines will change where they're locally tangent to the current velocity. So if I play this, we'll see that indeed the streamlines are time varying, and at any given snapshot it gives us a good description of the local velocity field, but we have to be able to construct the streamlines at every instant in time. That can be difficult to do unless the flow is steady.